Complex numbers are used in electronics to analyze alternating signals. We already explained this in our previous video. In this video, we are going to learn how to find the complex zeros of a quadratic equation, starting with quadratics with only real coefficients, followed by one with complex coefficient. We'll see how the roots of a quadratic link to the equation, and we'll master an exam type question. If our quadratic doesn't have a linear term, we can always take the square root. For example, when solving z squared plus 4 equals 0, we take the square root of negative 4, which is 4i squared. The imaginary unit I is here to help us evaluate square roots of negative numbers. Taking the square root of both 4 and I squared, we have found our two solutions, 2i and minus 2i. Notice that the solutions are equally far away from the origin and have opposite imaginary parts. In this second example, we are solving a quadratic with both linear and constant term. We use the quadratic equation with a equals 1, b equals negative 4, and c equals 5. Substituting these values carefully, the discriminant inside the square root, b squared minus 4ac, is negative 4. This has two complex roots, plus and minus 2i. Dividing both the real and the imaginary part by 2, we obtain 2 plus minus I. Our two solutions are equally far away from the origin, again, and their imaginary parts are the opposite of each other. Mathematicians call these complex conjugates. The question is, can we use the quadratic formula when the coefficients are not real? Stop the video here and have a think. Right, the answer is of course. When we derive the formula to solve a quadratic equation in our previous video, we didn't assume that the solutions were real. In our quadratic, a equals 1, b equals I, and c equals 12. The discriminant is negative 49, and this has two values, plus and minus 7i. Our first solution is minus I plus 7i over 2, and our second solution is minus I minus 7i over 2, 3i and negative 4i. Notice that these two solutions are not equally distant from the origin, as they are not a pair of complex conjugates. We could check that our solutions work by using the factors. If 3i is a solution, z minus 3i is a factor. If negative 4i is a solution, z plus 4i is another factor. Multiplying both brackets, we can see that the sum of the roots is the opposite of coefficient b, and the product of the roots is the coefficient c. We can use these rules in our favor. For example, if we need to write a quadratic equation with roots 3 plus I and 3 minus I, the sum is 6 because the imaginary parts cancel each other out. The product is 10. So the simplest quadratic has coefficients a equals 1, b the opposite of the sum, minus 6, and c the product of the roots, 10. Right. We are now ready to attempt the exam type question. We are given one root of the quadratic equation, 2 plus 4i, and we need to find the coefficients b and c of the quadratic. The clue here is that all the coefficients are real. If b and c are real, the complex roots come in conjugate pairs. If 2 plus 4i is our first root, we need 2 minus 4i to be our second root. This is so the imaginary parts cancel each other out, and we are left with real coefficients only. The sum is the opposite of coefficient b, and the product is the coefficient c. b must be minus 4 and c must be 20. The quadratic with complex conjugate roots is z squared minus 4z plus 20 equals 0. Complex numbers are very important. Master algebra and complex equations step by step. Visit mathsadviceonyourdevice.com for more details.